All right, ladies and gentlemen, welcome back to another video with Mr. Kenton for Physical Science. We are continuing our discussion and our walkthrough on chemical bonding. And today we're going to kind of look at a hodgepodge of things. We're going to look at chemical formulas. That's going to be one component. We're going to look at diatomic elements. That's the second component. We're going to look at polyatomic ions. And then we're going to look at our last type of bonding that can be there that it's kind of a mystery, if you will. It's metallic bonding. It's really not a mystery, but it's just kind of, it's different than ionic and covalent. And so it's not often very talked about. So, but we're going to start with looking at chemical formulas and being able to break those down and what kind of information should we be able to get from them just by simply looking at a chemical formula and why they're important, right? And so let's just dive right in here. We're looking at chemical formulas. Ultimately, what a chemical formula shows us, ladies and gentlemen, is it shows us the elements that are in the compound, which is useful because then we can look on the periodic table and find what they are. And the second thing it's going to do is it's going to show us what's the ratio of the atoms that are in this bond. So when we start to think about how is it structured at the atomic level, it's going to give us that ratio. Now, we look at something like H2O, right? Something that we're all very familiar with, right? This is water. We look at H2O and it's telling us something about its ratio. For every 2 hydrogens, there's 1 oxygen, right? And that little 2 there, that's a subscript, H subscript 2 O. That 2 is going with the H, just to make sure that we're clear here. There are 2 hydrogen atoms, and there's 1 oxygen atom. And so when we're looking at chemical formulas, it's always important to recognize that these little subscripts go with the element that precedes it, not with the one that comes after it, right? So there are 2 hydrogens, 1 oxygen, and anytime we're dealing with water, it's always going to have that chemical formula. Now that's useful because if chemists across the world want to be able to communicate with each other, it's good that they have these particular symbols so that when a chemist in the United States wants to communicate with a chemist that's in India or Japan or in Africa, if they want to communicate about elements, they already know how to do that because they have something that they're referencing. So it allows for just very easy communication. That's why chemical formulas and chemical nomenclature are so important. Now, here's another example of several other different compounds that you come in contact with on a fairly regular basis. Think of salt, for example, table salt, NaCl. That's going to be that's common. This is an ionic compound, right? And if we think about the ratio of our atoms here, it's 1 to 1, right? 1 sodium, 1 chlorine, right? We've already seen water. Water's covalent, at least in terms of its bonding. And as we saw in the previous slide, the ratio of elements is 2 to 1, right? 2 hydrogens for every 1 oxygen. Sand, so if you like going to the beach or you like playing beach volleyball or anything like that, is a compound called silicon dioxide, SiO2. This is also a covalent compound. And based on the ratios here, for every 1 Si to every 2 oxygens, right? 1 to 2. All right, sugar. For better or for worse, sugar's in a lot of different things. Candy, chocolate chip cookies, all that sort of good stuff. But sugar is an example of a covalent compound. And there we've got a ratio of, if we look at it from the whole numbers, that would be, I'm going to come over here to the left, 6 to 12 to 6. Or we could simplify that ratio. It's 1 to 2 to 1. Another way of thinking about that. You've got alcohol, like you just got alcohol here. That could be the alcohol that's found in beverages. Obviously, the alcohol that's in like rubbing alcohol is a little bit different. But here we've got another covalent substance because you got a whole bunch of nonmetals that are bonded together. So for this one, it would be if we're doing it with respect to carbon, hydrogen, oxygen, it's 2 carbons, 6 hydrogens, 1 oxygen, right? Because keep in mind, we just combined those to get that. And then magnesium hydroxide, so that's an ionic substance. And this is something that's commonly found in heartburn medications, because what it's able to do, it's able to neutralize acid because it's a base. So it's ionic, and if we start to look at our ratios here, it's going to be for every 1 magnesium, there are going to be 2 oxygens and 2 hydrogens, right? So that just allows us to kind of see the breakdown of the different types of atoms that are present there in those chemical formulas. Now, interestingly enough, you see a lot of the things that we encounter, at least on this list, 4 of the 6 are covalent. We do encounter some ionic substances and things like that, but it's just interesting to note that of those substances, 4 of them are covalent, 2 of them are ionic. Okay, so that just gives us a brief introduction and overview into chemical formulas, and we'll learn more a little bit later on how we actually write chemical formulas and come up with their names later. Now, let me shift gears here. Let's talk about what are known as diatomic elements. Now, what we can have happen, and if you think back to even the covalent bonding that we looked at, like with chlorine and hydrogen, you can have a covalent bond that occurs between atoms of the same element, right? And so when that happens, you get what's known as a diatomic element, right? It's a compound because it contains more than 1 atom, but the unique thing is it's the same atom that it's bonded to. And so if you think about this, diatomic, if we look at that prefix di, that means 2, right? So it's a 2-atom element. That's all we're saying when we say diatomic elements, a 2-atom element, okay? Now, on the periodic table of all, I guess now it's at 118 elements that are on the periodic table, only 7 of them are found this way. Only 7 of the elements on the periodic table occur as diatomic elements, right? And so those 7 are bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, and fluorine, right? So of all the elements on the periodic table, those 7 occur naturally as diatomic elements. And so what that means is that when you find them in nature, if you were to go and you were to find some bromine that was just lying around somewhere, it'd be kind of weird, but let's say you found it, right? You get natural bromine. If you look at its atomic structure, if you start looking at it at the particle level, it's going to always occur as 2 bromine atoms that are attached to each other through a covalent bond, right? And the same thing is going to be true of the other 6 elements that we've listed there, okay? Now, this is something my chemistry teacher shared with me. It helped me remember this. Maybe it'll help you. If you can remember either H, Brincloff, that's 1, right? Because if you can remember that kind of distinction, you now have the symbols for all of the elements that are diatomic. Or Brinkelhoff, that's another one that I've heard. I'll write that one down here. B-R-I-N-C-L-O. I said Brinkelhoff. So we need to make a slight change there. Brinkelhoff. I didn't actually mean to change it to a different color red there, but worked itself out. So if you can remember H. Brincloff or Brinkelhoff, or Brincloff, H. Brincloff, whatever, use those to help you remember, okay, if I see these elements, if I write their symbols, I need to write them as Br2, I2, N2, Cl2, H2, O2, H2, right? And Brinkelhoff works because it matches up with what we have right there. Okay, so those are your diatomic elements. All right, the next thing we're going to look at are what are known as polyatomic ions. And so even if we look at it, we see the word poly, we should kind of automatically go to, think about in English, poly generally means many, right? And then we got the word atom, so it's a many atom ion, right? So it's going to be an ion that's made up of multiple atoms. Okay, that's simple. And what we see is it's a group of covalently bonded atoms, so that's kind of neat. So the polyatomic ion is going to have covalent bonds in it, but it has an overall charge, right? So when they're bonded together, there's this overall charge that gets produced. Now, when you start to look at that, the implication is that when you look at just the polyatomic ion, so looking at kind of this first bullet point, think of this as just the polyatomic ion, right? So for this first bullet point, for just the polyatomic ion, if you look at the bonds within the polyatomic ion, it's covalent, right? But for the second bullet point, this is when the polyatomic ion is in a compound, right? Polyatomic ions are going to form ionic compounds, okay? Now, I've shown you over here on the right, this is a list of some polyatomic ions. And the really nice thing, ladies and gentlemen, is that on your reference sheet, there's actually a list of polyatomic ions that you need to know. If I'm not mistaken, the polyatomic ions you need to know specifically, so their formula and their name, are for ammonium, which is NH4+, nitrate, which is NO3 1-, sulfate, SO4 2-, hydroxide, OH-, phosphate, PO4 3-, carbonate, CO3 2-, chlorate, ClO 3-, and then acetate. Now that should have a minus sign on it, but C2H3O2 1-. Those are the only polyatomic ions that you guys are going to see in the scope of this particular class. So I would encourage you in your notes or something like that, I would write down each of those. I would start by maybe making 2 columns, and at the top of one column, I would write ion. The top of the second column, I'd write the name, and then what I'd go through and do, and I would just transfer NH4+ under the ion column, and then beside it, under the name, put ammonium. You know, nitrate, ion, NO3 1- under ion, nitrate under the name, right? So those are the polyatomic ions that you are personally responsible for. It's certainly on your reference table, but just want you to go ahead and kind of be aware of those and to check back with your reference table just to make sure. Okay. Now, we're going to make a brief comparison here because we've gone through, we've looked at ionic, and we've looked at covalent bonding. And so I'd like to compare just the two so we can see the differences between them, because we do see some very unique properties for each of these different types of substances, right? So if you think about it, for ionic substances, when we think about what's going on with the electrons in an ionic bond, electrons are transferred from a metal to a nonmetal. So I see this as a good summary slide for everything we've done up to this point, okay? So this might be good to kind of review and kind of write this down in your notes and say, okay, we've done these things. This is kind of the key pieces of information from some of the previous slides that you need to be able to remember. Now, if it's covalent, it means we're sharing electrons between 2 nonmetals, right? Shared between 2 nonmetals, right? I'm gonna just put that there. Now, melting points, as a physical property, ionic substances have a very high melting point. Typically, it's like above 1,000 degrees Celsius. Some can be lower, but a lot of them have high melting points, higher melting points than usual. Covalent compounds have relatively low melting points. Think about water, for example. It melts at 32 degrees Fahrenheit, 0 degrees Celsius, so relatively low. You know, soluble in water. Remember that idea, soluble means that it dissolves, right? So if it dissolves in water. For ionic substances, it's a resounding yes. For our covalent substances, usually not the case. All right. Do they conduct electricity? Do they have the ability for electrons to move within them? For your ionic substances, when they are in the liquid state or when they've been dissolved in water, then ionic substances can conduct electricity. Your covalent compounds, they do not. And then some other properties to consider. We saw how ionic substances have a crystal lattice of ions and form what are called crystalline solids. Whereas your covalent substances, they're molecules, they tend to be smelly, and they tend to be liquids and gases at room temperature, right? So from this little comparison chart, we can see some big differences between ionic and covalent compounds, but they're things that we should be able to recall and be able to identify should we be asked to. And then the last thing we're going to look at today, ladies and gentlemen, with this video is metallic bonding. So we've looked at ionic, where you've got a metal and a nonmetal. We've looked at covalent, where you've had two nonmetals. But there are instances where there will be bonds between two metals, right? And so that's when we get metallic bonding. So bonding between metals, that means you're going to be dealing with elements that are generally located on the left-hand side of the periodic table. Now, what we find is that when we see the bonds in metallic substances, we describe it as a sea of electrons. And what I mean by that is if you look at this image down here, you've got these electrons that are here, here. I'm just going to draw circles around all of them, right? Right? You got all these electrons. And instead of each electron being owned or attached specifically to one of these metal ions that are kind of the gray spheres, what we see is that these electrons have the ability to just kind of freely move throughout the substance, right? So they're able to move, they're moving around, and they're going to continuously move. They're not just going to stay in one spot. And so what we start to see is that the charge gets distributed evenly over all the metal atoms. And so because of that continuous motion, that's why we call metallic bonding, or describe it as a sea of electrons. And again, that's because the electrons are just continuously moving around the metal. Now, I don't anticipate you seeing much about metallic bonding. Honestly, if you see something, it's probably going to say, how would you describe the bonding? And you just simply use the phrase sea of electrons, and you're probably good to go. All right. Well, that, ladies and gentlemen, takes care of chemical formulas, diatomic elements. Remember Hofbrinkel, or Brinkelhoff, or H. Brinkloff. It deals with our polyatomic ions, and we just introduced metallic bonding. All right. So if you have any questions, please don't hesitate to ask in class. Feel free to shoot me an email, fill out the Google form, or bring your questions to class. I'd love to answer any questions that you guys have. Thank you for joining me. I'll see you guys again soon.